Assalamu alaikum dear students. This is lecture number 13 of week 7 for the course Electronic Design and Practice. Today's topic is Op-Amp Basics. This is section number 10.4 of chapter 10 Operational Amplifiers for the book Electronic Devices and Circuit Theory. And we have introduced op-amps in earlier lectures, in which we have concluded that op-amp is basically an IC, and it has two inputs and one output, and have two power supply connections. These two terminals serves as the input to the op-amp, and we can apply input on either terminals or at both terminals, that is V in 1 and V in 2, and we will get output from pin number 6. That will be the amplified version of these two inputs, and the gain of this amplifier is defined as the differential gain AD, and the differential gain of the op-amp is very large. And another gain we defined as the common mode gain for the common mode inputs, and the common mode gain is AC, and the value of AC is very small, and the ratio of differential gain to the common mode gain is called the common mode rejection ratio, and typically the common mode rejection ratio of the op-amps is a very large quantity, and that specifies that the amplifier would amplify the differential signals pretty high as compared to the common mode signals. So this was the differential amplifier, and it has two inputs and have two outputs, and out of these two outputs any one of them can be taken as the output of the differential amplifier. Next is we are still in the introductory phase, and we are learning the op-amp terminologies and basics in introductory lectures. And in this lecture as well we would introduce some other quantities related to the op-amp, and towards that I am now going to introduce the another important quantity, that is called the input impedance or input resistance of the op-amp. And the input resistance of the op-amp is defined as V in 1 over I in, where I in is the current flowing into the input terminal of the op-amp, and similarly Ri is defined at the other terminal, that is V in 2 divided by I, where II is the input current flowing into the input terminal of the op-amp. So we can represent the input impedance of the op-amp as the input resistance between these two terminals. If voltage is applied at the input terminal, then how much current that would flow into the input terminal would be the magnitude of that current would be defined by this input resistance. Similarly, if I apply voltage here and keep this terminal at ground, then what would be the magnitude of the current that would flow through the into the input terminal? That would be limited by this input resistance of the op-amp. So whenever there is a input signal applied to the inputs of the op-amp, with the application of the input voltage, a current would flow into the input terminals. So for these BJT transistors, when you apply the input signal, then there would be always be a signal current that would flow into the base of the transistor. So magnitude of this current and the voltage, the ratio of these two would define the input resistance of this op-amp. So typically the input resistance of the operational amplifiers with BJTs at the input stage would be typically in mega ohms range. It is quite large, but if you have differential amplifiers implemented with the MOSFETs rather than BJTs, this input impedance would even be very large as compared to the op-amps with implemented with BJTs, because the MOSFETs would not take any input current from the gate of the MOSFET. MOSFETs have very high input impedance, so ideally the op-amp should have as much high input impedance as ideal. So MOSFETs would exhibit much better input impedance characteristics as compared to the BJTs. Symbolically we can represent the input impedance of the amplifier between these two input terminals Ri, and this input impedance is quite large for practical op-amps. So there is another impedance we can define at the output side, and the output impedance would be defined as the ratio of output voltage and output current, and the equivalent voltage source at the output side, a Thevenin equivalent, that we have usually model amplifier with these three parameters: input impedance, output impedance, and a dependent voltage source, and where this dependent voltage source value is gained into the input of the amplifier. So from this is the basic structure of the equivalent circuit of op-amp. So this structure is very important. So we have reduced the complex circuit of the op-amp in which there were many transistors connected within the IC, and we have we are not going into the details of the internal circuit, but we would be just look at the op-amp operation from the input terminals and from the output terminals. So we have simplified the circuit of the op-amp into this equivalent circuit model. So if you even if we did not go into the internal details of the op-amp, we can just you see the op-amps from the terminal point of view and still use the op-amp from terminals characteristics, and use the op-amp in many applications. And this circuit is the simplified circuit that we can use to study the operation of the amplifier from the terminal point of view. So from terminal point of view, we have number one, the input terminals, and the second is the output terminal, and these two power supply connections. So from the external side, op-amp has these five important terminals that we can use these terminals and apply these terminals for the input and output side and power supply connections, and use this op-amp to perform different functionalities, like we can use it as an amplifier, as a summing amplifier, difference, and much more applications. So it is very important to know how this device or module would be when we are using it from the terminals, and for that how it behaves from the input side when we apply signals, and how much the input impedance that it will offer. And again, if we look at the from the output side, and I am going to connect a load, then how this amplifier would be loaded from the output side, and how much the output impedance that it will offer, and how much gain the amplifier would have. Secondly, what are the power supplies connections, and what are the output levels when we are connecting a certain amount of power supply at the output, at the supply terminals. So with the introduction of these input and output impedances and the gain of the amplifier, we can characterize an open from these parameters as the op-amp has a finite input impedance, and it is in the range of mega ohms. So input impedance has a finite value, and it would be, for practical op-amps, it would be in mega ohms. It would be quite large. The non-zero output impedance, the op-amp output impedance would be of non-zero value, and it would be few ohms, and in the range of 10 to 20 ohms. So output impedance or output resistance would be quite low, whereas the input impedance would be quite high. So what would be the importance of having input impedance high and output impedance low, that we will later on see. So the op-amp should have the input impedance very large and output impedance very small. So the op-amp has a finite voltage gain, and it is of a large value, and it is around about 2 into 10 to the power 5 for LM741 op-amp. So from these characteristics of the op-amp, from the terminal point of view, we can idealize an op-amp. So what should be an ideal op-amp is, the ideal op-amp is the one in which the input impedance should be infinite, and the output impedance should be zero, and voltage gain should be infinite, and no current flows into the input terminals. So when you apply an input signal, the current flows through the input terminal should be very small, and ideally it should be zero. So zero current should be flowing through the input terminals. So an ideal op-amp should be having input impedance very high, approaching infinity, and output impedance should be very low, approaching zero, and gain should be very high, approaching infinity. And as a result, when you apply the input signal, then no current would flow, because input impedance is infinite, being input terminals appears as an open, and if there is no resistance at the input, then current would remain zero. So few op-amps which are made with MOSFETs, so they exhibit very high input impedance, so they did not take any input current for a voltage at the input. So this is the structure. This is the simplified block diagram or equivalent circuit of the op-amp, in which input impedance is shown here, and input signal is applied at the input side, and a load is connected at the output side, and output is taken from the op-amp. And for this equivalent circuit, the ideal model would be this one, in which there would be no input impedance. The input impedance is infinite, and output impedance is zero, and gain approaches infinite. So ideally infinite internal resistance, zero output resistance, and gain is very large, approaching infinity, and in is 0, no current flows into the input terminals, input current is 0. So practical op-amp has certain finite input current, and for ideal op-amp the input current is 0. Next is how much an op-amp amplifies. So what would be the what is the gain of the amplifier, and what I will get at the output if I apply an input signal and having a gain being very high. So assume that the gain of the amplifier is this much, 200,000, and I want to find out the output for this op-amp, and I apply a signal at the input, for example of value V in equal to, for example, 1 millivolts. So for example, this input has a magnitude of 1 millivolts peak value. Then with the gain of 200,000, what I will get at the output. So for that, to find out the output, I know output is equal to gain into the input Vd, the gain to the difference signal, where Vd is equal to V1 minus V2, and I am assuming here, note that I am not taking any common mode gain or common mode output. So because I am assuming that this op-amp has a large common mode rejection ratio, and the common mode gain is very small, so I am assuming it is negligible. So only taking the differential gain, and differential gain is given, and Vd I can compute from this equation as V1 minus V2. So V1 is this voltage, which is for example 1 millivolt peak, and so V out is Vd is equal to V1 minus 0, V2 is 0, so Vd is equal to 1 millivolts. So gain would output would be equal to gain into Vd is 1 milli. So when I compute this value, the output would be equal to 200 volts. So if I apply 1 millivolt here and amplifier as a gain of 200,000, I will get an output equal to 200 volts. So can output be 200 volts? So this is the question. So you can see that the op-amp is biased with these power supplies. So for an op-amp or any amplifier, the output voltage level cannot go beyond these power supply levels. So for any amplifier, whether it is an op-amp or any ordinary transistor amplifier, the output would always be limited by these power supply levels, which are used to bias the amplifier or bias the transistor. So students, जो op-amp की जो आउटपुट है वो कभी भी सप्लाई जो वोल्टेज सप्लाई वोल्टेजेस हैं इनसे कभी भी ऊपर नहीं जा सकते. सो यहाँ पे जो आउटपुट पे मैक्सिमम वोल्टेज आप ले सकते हैं वो आप या तो प्लस VCC ले सकते हैं मैक्सिमम, या इससे कम आउटपुट आ सकती है, या माइनस VCC तक आपकी आउटपुट जा सकती है मिनिमम, या उससे कम रह सकती है. सो फॉर एग्जांपल मैं अगर यहाँ पे VCC अज्यूम करता हूँ 15 वोल्ट यहाँ पे और यहाँ माइनस 15 वोल्ट, तो आउटपुट कितने पॉसिबल हैं? मैक्सिमम 15 वोल्ट्स आ सकते हैं, इससे ज़्यादा नहीं जा सकते, मतलब 16 वोल्ट्स पे नहीं जा सकते. इवन 15.1 तक की वोल्टेज, आउटपुट की वोल्टेज 15.1 तक भी नहीं जा सकते. इस तरह से अगर यहाँ पे मैं माइनस 15 वोल्ट्स सप्लाई कनेक्ट करता हूँ तो आउटपुट कभी भी माइनस 15 से नीचे नहीं जा सकते, मतलब माइनस 16 नहीं पॉसिबल. सो ये जो सप्लाई वोल्टेजेस हैं ये op-amp को आप पावर अप करने के लिए यूज़ कर रहे हैं, तो इसकी भी एक सर्टन लिमिटेड मैक्सिमम वैल्यू स्पेसिफाई होती है डाटा शीट के ऊपर. सो फॉर एग्जांपल 741 op-amp के केस में जो आप मैक्सिमम सप्लाई यहाँ पे कनेक्ट कर सकते हैं वो प्लस माइनस 22 वोल्ट्स तक मैक्सिमम अप्लाई कर सकते हैं. कुछ ओपन में आप 25 वोल्ट भी अप्लाई कर सकते हैं, 30 वोल्ट भी अप्लाई कर सकते हैं, मे बी 50 भी अप्लाई कर सकते हैं, but it cannot be very high. It cannot be 100 to 200 and so the keep this thing in mind that output voltage level would be limited by these supply voltage levels. So if I am applying 1 millivolt at this point, and gain is 200,000, then output should be 200 volts, but 200 volts are not possible for an op-amp having supply voltages of, let's say, plus minus 15 volts. So output cannot go beyond 15 volts. So 200 volts output is not possible. So what happens is for a 1 millivolt signal, output would be in saturation, and it would be saturated at this supply voltage level 15 volts. So if I apply let's say minus 1 millivolt here, then VD would be equal to minus 1 millivolt, minus V2 is 0. So VD would be equal to minus 1 millivolt, so output equal to 200,000 into minus 1 milli, and the result would be minus 200. So if for our minus 1 millivolt here, output would be only at minus 15 volts, and output would be saturated at this value. So how much the output level could be? So the maximum output voltage that we can achieve is plus minus 15 volts. So due to the large gain, output is always saturated even for a small input signal. So you can see that for a very small input signal of 1 millivolt, you will be getting an output of 15 millivolts. So even if you reduce the input level to half millivolt, so for half millivolt, what would be the output? It would be 100 volts. Still 100 volts is not possible at the output, and you will be getting only plus 15 volts. So half millivolts, 1 millivolt would for 1 millivolt output would be at 15 volts. For half millivolt it would be again at 15 volts, and even you further reduce the input to a quarter, let's say 0.25 millivolts, 0.25 millivolts, the output would be equal to 50 volts. Again, output cannot be at 50 volts. Output would be saturated, and you will get 15 volts. So for any input of even in millivolts, you are getting the output at saturation. So due to the large gain, output is always saturated even for a small input signal. So from here there could be a question that how much we can apply at the input signal, that is how much the input signal level should be so that the output voltage remains below plus minus 15 volts. So यहाँ पे मैं कितना इनपुट सिग्नल अप्लाई करूँ कि मेरी आउटपुट 15 वोल्ट्स या इससे कम रहे, तो उसके लिए हम देखते हैं कि अभी उससे पहले अगर आप देखें कि मैंने एक सिग्नल दिया था 1 मिलीवोल्ट का, और जो मुझे आउटपुट मिलेंगे वो इनपुट जो ही थोड़ी सी भी बढ़ेगी, लेट्स से आपने देखा था 0.25 मिलीवोल्ट्स भी हो जाएगी, तो भी आउटपुट सैचुरेशन में 15 वोल्ट्स रहेगी. सो फॉर इनपुट वैल्यू ऑफ फ्रॉम 0 to 1 millivolts, in this range output would always be in saturation. Similarly, when input goes in negative region, so again output would be in negative saturation, and when input goes positive, output goes into positive saturation. So if you apply a very small input sine wave, then output you are getting is a square wave. So amplifier this op-amp with the very large gain, very small input sine wave, for a very small input sine wave you are getting a square wave. So this op-amp is this op-amp is amplifying with a very large gain, and so that output always remain in saturation, and for sine wave we are getting square wave. So what this op-amp is doing, it is amplifying very enormously high, so that we are not getting the sine wave at the output for a sine wave at the input. So output is distorted. So what this op-amp is doing is, this is not giving me the sine wave at the output for a sine wave at the output. So for the amplifier it is essential that sine wave, the shape of the signal shape of the input signal should retain, and for a sine wave input I must get a sine wave at the output. But this signal, this op-amp is not producing the sine wave, rather it is producing square wave, and that means this input signal appears at the output very distorted. So for an amplifier the signal should not be distorted, and I must get a clean sine wave, amplified sine wave at the output. So the question is, for an op-amp with a sine wave at the input, can I get a sine wave at the output? So for that I would like that this op-amp should not go into saturation. So for that I have to limit my input signal to a very small value, because the gain is very large, so that the output doesn't go into the saturation level, that is output remains below plus minus 15 volts. So how much the input signal level should be so that the output voltage remains below plus minus 15 volts, and I get the sine wave at the output. So for that I can compute the input voltage level from this equation. Vout is equal to AD into VD, and from which I can find out VD, that would be equal to Vout over AD, where Vout should be less than or equal to plus minus 15 volts, and AD is the differential gain, which is 200,000. So from this equation I can compute value of VD is equal to plus minus 75 microvolt. So if VD is less than or equal to 75 microvolts, then with this gain output would be less than or equal to plus minus 15 volts. So the input to an op-amp must be kept below this level to get undistorted output. Next, so it means we can only use op-amp as an amplifier if input signal is very small, that is less than or equal to 75 microvolts. So if the magnitude of the input goes above 75 microvolt, the output will go into saturation and will be clipped and get distorted. So the situation will get even worse. For example, if the gain of the op-amp is even higher than 200,000. So for example, if gain is further high for an op-amp, which is 10 times, for example, higher than 200,000, then the input signal should be 10 times smaller than the value of for the gain of 200,000, that is it should be less than 7.5 microvolts, and with this gain the only 7.5 microvolt would be enough to make output saturation or output saturated. And for an ideal op-amp with infinite gain, so if gain becomes infinite, then any value divided by infinity would result in 0, that is the signal magnitude would even be close to 0, approaching 0, So for a very small input that is close to 0 would bring the op-amp into saturation, which implies that with approximately 0 input the output would be in saturation level. So this is the problem we have seen in the op-amp, that we are idealizing the op-amp, that op-amp gain should be very high and approaching infinity, but the problem is the input signal should need to be kept very small, so that output magnitude remains undistorted, or op-amp should not go into saturation, and we can use the op-amp as an amplifier. So op-amp as an amplifier, how can we use the op-amp as an amplifier that with a gain of very large value, and we have to keep the input signal very small. What that means is we can only apply signals of microvolts at the input to get an output which would be undistorted. So this shows that op-amp cannot be used as an amplifier with this large gain, because the input signal we have to keep it in microvolts range, which is a very difficult task, that keeping the input signal in microvolts is very sensitive, signal becomes very sensitive to noise, and it limits us for the range of the input that we want to amplify. That means we cannot amplify signals having magnitudes of millivolts or in the volts range. So how I can use the op-amp for the signals of the range in millivolts or in volts to be used and amplify them using the op-amp. So we have to reduce the gain somehow, and let me see कि हम op-amp को किस तरह से यूज़ कर सकते हैं. So पहली बात ये है कि हम चाह रहे थे कि op-amp का जो गेन है वो बहुत हाई होना चाहिए. Ideally it should be infinity, but this high gain becomes problematic for us, that we cannot use the op-amp with this very large gain. So somehow we have to reduce the gain. So on one side we were trying to improve the gain of the amplifier, and now we are saying that we have to reduce the gain of the op-amp. So these two things are getting contradictory, but as we will move on, we will see that the idealized situation will help us in the stability of the op-amp, or the characteristics of the op-amp would be pretty much we will get a very better performance from the op-amp with the idealized high gain. But somehow we have to use the op-amp, so we have to reduce the gain of the amplifier. How we will reduce the gain of the amplifier? The gain is reduced by applying the feedback to the amplifier. So the gain is reduced by applying feedback to the amplifier, more specifically negative feedback. So feedback का मैं आपको concept दूंगा कि feedback क्या होती है और उसमें negative feedback क्या होती है, positive feedback क्या होती है, इसके क्या impacts होते हैं. So you will see the negative feedback reduces the gain of the op-amp. So in order to use an op-amp as an amplifier, negative feedback must be applied, otherwise you cannot use the op-amp without negative feedback. You cannot use the op-amp as an amplifier. So feedback is for feedback in op-amps is in order to reduce the gain, op-amp is used in closed loop configuration. That you can see in this figure. For that, a signal is fed back from the output to the input. So this is the amplifier. It has this input Vd and output V0, but as this amplifier simply in the open loop cannot be used as an amplifier, so we have to use it in feedback. So for the feedback, we fed back an output signal. We take an output signal and feed it back to the input side, and this amplifier now becomes a closed loop amplifier in which a feedback is now applied, and this amplifier is in feedback. So the gain of the op-amp with feedback is called the closed loop gain. So this amplifier now has a new gain, and that gain is called the closed loop gain of the amplifier. So the differential gain AD is called the open loop gain. This AD is called the open loop gain, and when this amplifier is connected with feedback, and you compute new gain V out over V in, that new gain would be now the closed loop gain of the amplifier. So we have feedback systems. There are two types of feedbacks. One is called the positive feedback, and the other one is called the negative feedback. These two figures classify the positive and negative feedbacks. Positive feedback is the one in which the output signal is feedback and added with the input signal. So this output signal would be added with the input signal, and that the addition of these two is applied at the input of the op-amp as a differential input. So this configuration is called the positive feedback configuration. The other one is the negative feedback. In negative feedback, you take the output signal to the input side and subtract it from the input, and the subtraction of the difference of these two inputs is applied at the input of the op-amp, and this configuration is called the negative feedback configuration. So this is a negative feedback in amplifier, and this negative feedback would reduce the gain of the amplifier. So closed loop gain of this amplifier would be very smaller, less than the open loop or differential gain of the amplifier that we will see in the next class, inshallah. Thank you, students. Thanks for today. Allah Hafiz.